Hi everyone, I'll be presenting our work, Multi-Modal Manipulation via Multi-Modal Policy Consensus. In this example video, our robot is performing a puzzle insertion task. I need to grasp two puzzle pieces, one after another, and insert them into puzzle board. So how are we able to achieve this? The robot is equipped with tactile sensor and two RGB cameras, as shown on the screen beside it. The task is particularly challenging because it requires the robot to combine vision and touch. Vision helps robot localize the puzzle pieces. Touch enables it to feel the contact and guide precise insertion. Even if a human swaps the position of the puzzle pieces, the robot can adapt and complete the task successfully. Now let's take a look at a human example. When a person is trying to find a marker, they might look around first to locate it visually. If the marker happens to be inside an opaque bag, the person will then reach in and search by touch, even without seeing what's inside. This shows that how humans naturally integrate vision and touch, using vision to guide where to search and touch to confirm and feel the object when vision is unavailable. So how did the previous work approach this problem for robotics? A long-standing method originally proposed in 2017 and still widely used today is to handle multiple modalities by simply feeding each modality into its own encoder. Each encoder produces a latent embedding, for example, one for vision and one for touch. These embeddings are then concatenated and passed into a policy decoder, which outputs the robot action. There are two major issues with this traditional fusion approach. The first issue is sparsity. Imagine we have 100 demonstrations, but only a few frames, say like 5 frames, actually contains useful tactile data. Since the baseline method trains all modalities jointly, the dense visual data dominates the learning process and the sparse tactile signal gets overwhelmed. As a result, the model tends to ignore the tactile input even though it could provide critical contact information for precise manipulation. The second issue is inflexibility. If you want to add or remove a modality, say introduce audio or remove depth, you cannot just adapt the network. You have to retrain the whole thing from scratch, which makes it impractical in real-world setting where sensors changes. Motivated by how human brain processes information, we know that different regions are specialized for different functions. For example, the visual vertex for vision and the somatosensory vertex for touch. These regions operate independently, yet they collaborate seamlessly to form a unified understanding of the world, integrating what we see and what we feel. The key insights of our work is to avoid blindly concatenating all modalities into one monolithic policy. Instead, we model each modality, such as vision, touch, or audio, with its own expert distribution that captures what that modality knows best. The overall policy is then formed as a product of these expert distributions, allowing the robot to combine information probabilistically rather than by simple fusion. Our approach addresses this sparsity problem through modality-specific expert. For each modality, such as vision, touch, or audio, we learn a separate action distribution that is conditioned only on that modality. This means that even a modality provides very sparse signal, it still has its own expert that can learn from and represent that signal effectively. Our framework also enables flexible composition even when new modalities are introduced. If a new modality becomes available, for example, adding audio or depth, we can simply learn a new expert distribution for that modality. Then we multiply it with the existing expert using the product of expert formulation to form an updated final action distribution. This design allows the policy to adapt easily without retraining everything from scratch, making it scalable and modular for real-world robotic systems. Here is a concrete breakdown of our method. We start with sensory inputs such as images or other modality signals. Each input is passed through its own encoder to obtain a latent embedding. This embedding are then fed into a factorized diffusion policy, where multiple diffusion heads capture different aspects of the information, for example, local details and global context. We apply the same process to other modalities, so each has its own encoder and diffusion-based expert that models its action distribution. Next, we take the embedding from all modality and feed them into a router network. The router's role is to compute the consensus weights and decide how much each modality should contribute to the final policy. After weighting and combining the modality experts, we perform denoising over multiple iterations, following the diffusion process to gradually refine and generate the final action output. One question people might ask is feature concatenation itself the policy bottleneck? To explore this, we compare three models. Feature fusion, the standard baseline that concatenates modality features. Factorized MOE fusion, still use feature concatenation, but with multiple action heads to increase policy capacity. Our method, which model each modality as an expert and combine them with a policy consensus. We evaluate this model on multitask RL bench. These results show that simply adding more action heads does not significantly improve policy performance, since feature concatenation limits the policy ability to use multi-modal information effectively. In contrast, our model achieves a larger performance boost, demonstrating that modality-wise factorization and consensus provide a more expressive and adaptable policy structure. Let's take a look at whether our framework allows the robot to adaptively shift its focus across modalities. We analyze this using perturbation-based importance analysis. Initially, during the searching phase, the robot relies primarily on RGB stream to locate the bag. Then, in the grasping phase, it begins to use both vision and touch, combining what it sees and feels to grasp the marker accurately. Finally, in the placement phase, it places the marker into the bin, completing the task smoothly. Our policy is not only able to complete the task successfully, but also to do robustly under sensor corruption. For example, even when we block one of the RGB cameras with a black card, the robot continues to perform the task correctly. We also evaluate our policy robustness under real-time perturbation. In this example, after a robot successfully retrieves a marker from the bag, a human intentionally snatches the marker away twice during the task execution, creating unexpected perturbation. Despite of these interruptions, the robot adapts its behavior, replans, and successfully completes the task, showing strong reactivity and resilience in dynamic real-world settings. Finally, we combine both human perturbation and sensor corruption in a more complex spoon reorientation task. In this task, the robot first grabs the spoon and then reorients it and places it into a dish rack. After that, a human resets the environment by moving the ball into a new location, while also blocking one of the RGB cameras with a black card. Even when this simultaneous disturbance, the robots adapt to the new configuration and successfully complete the task, showing strong robustness and generalization in dynamic multimodal conditions. Our framework also supports incremental learning. In this experiment, we first train two separate policies, one using RGB input and another using tactile input. Then we combine them using manually specified consensus weights without joint training. Surprisingly, the robot still compose its independent learner skill, effectively integrating tactile feedback into its behavior, demonstrating that our framework enables modular and incremental policy learning across modalities. Of course, our method is not without limitations. Under severe sensor corruptions, the policy can sometimes fail. For example, when one of the cameras is completely blocked or degraded, the robot may become confused about the object location or lose depth and distance information when relying on a single monocular camera. These issues can lead to reduced accuracy or incomplete task execution, highlighting the opportunities for future improvement in sensor corruptions. In summary, the key takeaway from this work is that our compositional policy enables sparsity-resilient, incremental, and adaptive multimodal manipulation, seamlessly integrating new sensors without retraining. It retains and leverages sparse but informative signals. It has a modular design which allows independent training and easy composition. It has also shown robust performance in real world, even under perturbations and sensor corruptions.